All right, so another cold day in Champaign, but thank you guys for coming. So today is the 10th lecture in this course. And we are going to be discussing logistic regression. We're going to be discussing classification. So maybe I'm going to change the title a little bit. We're going to be discussing classification and logistic regression. Okay, and so we're going to talk about linear classification. We'll discuss the weaknesses of linear classification, logistic regression, and support vector machines. So let's begin. All right. So previous lectures, we talked about linear regression. We talked about linear regression, fitting a linear model so that it matches the data. And the hope when after you fit a linear model to a set of data is that you could export the model later. And when you have a particular input, you could predict what you expect the output to be, right? That's the goal of all of this. We have some set of data which we'll train a model on, and then in the future, we're going to get some new inputs, and hopefully we could predict what the outputs for those new inputs will be without knowing it, without actually going through and measuring it and doing all of that. Okay. But most data, we talked a lot of it, like the data we were considering, it was a continuous input and you had a continuous output, right? You had an output that was between between 0 and you had an input that was some range of numbers and you had an output that was some range of numbers. So a lot of data is not like that, of course. A lot of data is just classes. It's just a binary. It's something like gender, race, species. All these things are not elements on a continuous axis. They're just classifications, right? So we need to be able to produce classifications. We need to be able to fit models to classifications. To predict zeros and ones, yeses and nos, and all of that. So the next two lectures, we're going to talk about classification and classifiers. Okay, so since we were doing linear models before, let's keep the theme going and do a let's do classification using a linear model now. So classification, we define classification as predicting a discrete value target. And in our case, we're just going to do binary classification. We're going to extend this to multiple parameters later on. But let's suppose we have a bunch of training examples with some inputs, and we have some targets. And we have a binary classification, which means that for some sets of inputs, the target is one of the class 1, and for the other set of inputs, the input is class 0 or a negative example. Okay, so we define a linear function, a linear classifier, using this linear function like so. But we put another layer on top of it by saying if this function exceeds a certain value, we output a 1. If it doesn't exceed that value, we output a 0. Right? Makes sense. So there's a way to simplify this model. There's a way to simplify this model. Namely, if we want this model to be greater than or equal to some arbitrary value r, well, that's really the same thing as wanting this model to be greater than 0, but just shifting r over to the other side. Okay? And really, when you have two constants here, you have a bias from the original model, and you have a new constant, r, which is like the classification threshold, I mean, you don't really need these two things separately. You could just combine them to get a single value, right? We'll call this bias prime, right? So first thing we do is eliminate the threshold because it's not really helping or doing anything. We'll just simplify our work that way and just say binary classification is when the linear model is greater than or equal to 0, we output a 1. If it's less than 0, we output a 0. Okay? And then we do what we did in the previous lecture, which is eliminate the bias. Well, we don't really eliminate the bias. We just sort of make the notation cleaner, even with the bias, and just say that x0 always takes the value of 1. And so W0 would always we just say that's the bias. Okay? If the column x0 is always equal to 1, then W0 is equal to the bias, and then the next columns are the actual inputs. Okay? And then so we have this model, we have our linear model, which is the same as we saw last lecture. Z equals W times X. I put transpose there. I mean, it depends on how you define the matrices. And then again, the classification is like one layer on top of it, which is if the linear model exceeds 0, we output a 1. If it does not exceed 0, we output a 0. Make sense? So basically, this is a sine function. If the sine of z, we just say y is equal to the sine of z. Actually, that may be a good thing to put down. Test case is y, which is equal to there we go. No. I'll just do that. Okay. A lot of textbooks and lectures write it as just the sign of a particular variable. Okay. But I don't necessarily do that always. Okay. So does all that make sense? We start off where we were, very basic linear classification model. We just add, very basic linear model. We add sort of a classification layer on top of it. We simplified a linear model, and then we get to as simple a model as we could possibly get. Okay. So next, let's classify some functions. Let's use the linear classifier to classify some functions. And namely, I would like to classify knots. Okay? This is just a nice little exercise to show you linear classification could be used in a multitude of ways. Namely, we have a particular input. We have a particular input. X1 is the input, by the way. X0 is a bias. Remember that. And we have X1 is class 1, and when X1 is 0, we have to output a 1, and when X1 is 1, we have to output a 0, right? And we have to use a linear classifier to classify this, right? So what do we do? Well, when X1 is equal to 0, that means there's no W, so then the bias has to be greater than 0. When X1 is equal to 1, we have to have 0 or less than 0, which means the bias plus the slope has to be less than 0. Right? So there are multiple solutions for this, of course, but the nice simple solution is if the bias is equal to 1 and if the slope is equal to -2, then you are able to classify this knot function perfectly, right? Because when X1 is 0, then the whole function is equal to 1, so you get a 1. When X1 is 1, the whole function is equal to 1 minus 2, which is equal to -1. So you get a -1, which would be our 0 case with binary classification, right? Nice little trick there. Let's go on to the next one. There we go. So, actually, I'll hide it a little bit. I'll hide the solution a little bit. Let's work on it. So, let's say we have the and function. we have x1, x2. We have two inputs. x0 is, of course, the bias, so we just put 1 all the way there. So we have x1, x2, and the output is 0 unless x1 and x2 are both 1. Okay? So if x1 and x2 are both 1, we want it to output a 1. Otherwise, we want it to be 0. Or let me rephrase that. When x1 and x2 are both 1, we want the output of the linear function to be greater than 0, which would give us a 1. And when that's not true, we want the output of the linear function to be less than 0, which would give us a 0. So what should we assign the values of b, w1, and w2 equal to get a linear classifier working for the and function? What do you guys think? Yeah, please. Yeah. Yeah, I think that works roughly correctly. Well, let's see. Well, I should have said, so if b1 and if b1 is equal to 1 and w1 and w2 are both equal to 1, then if for this case, if one of them is equal to, for these cases, the output of the linear function would be 0, exactly 0. So depending on how we define this, I mean, we did define this correctly, I want to say. No, we didn't. Wait, how do we define the linear? Was it exactly, what was it? Oh, yeah. So because we defined this as if the z is equal to 0, then we output a 1 still. Then if b is equal to 0, basically if w1 and if b is equal to -1 and w2 and w1 and w2 are both 1, then for this function, then we would get 0 and we get at a 1, right? But it's easy to fix because we could have just shift it and say b is equal to what do you say? B is equal to -1 or 1? You made b negative? Oh yeah, I mean that still works, but yeah, it still works. So, I mean, if we do what you did, so if b is equal to 1, w1 and w2 are -1, then at 0 this would equal 1, which would be all three of these, which would be a NAND function. Not a big deal because then you could shift b up or you could shift b down. You can make b 0.05. Yep, that works. You can make b 0.05 and w1. 0.05. You can make it 0.5. And w1 and w2 both equal to -1, and that would work. Or you could do, I mean, in this one, I'm doing it from the reverse direction. b is equal to -1.5. w1, w2 are equal to 1. And so the only way w1 and w2 are, the only way to get a positive value is simply for both of these to be positive, for x1 and x2 to both be equal to 1. But that makes sense. Everyone, it's just a reverse logic. Yeah, please, Naomi.
For the b function that we have set to 2, would that be greater than or equal to 0 based on our definition earlier where like we have y equals, if it's 1, if z is greater than or equal to r, and the 0 of z is less than r?
Can you say that again?
So like above we defined our y equals 1 if z is greater than or equal to r, and then
Yeah.
z is less than 0.
Yeah.
For 0, so then would we be able to then make this, what was it, b plus w1 plus w2 greater than or equal to 0?
Oh, greater than or equal to 0?
Yeah.
Oh, yeah. Typically, you want to avoid sort of the boundary conditions, and it becomes an issue with differentiation. PyTorch has an issue when you go right up to the boundary conditions, or actually right on the boundary conditions, differentiation becomes annoying. So typically you want to try your best to avoid those boundary conditions. So that's why I'm just doing it like this. But yeah, that's in the theoretical sense, perfectly valid. In the practical sense, you might run into a slight issue, but you know, that's the problem for tomorrow. Yeah. Any other questions? All right, good. So, XOR. I didn't put anything down. What do you guys think? How do we define B, and M? B, M1, and M2, right? Two inputs, yeah. Yeah, two inputs. Yes, please.
It doesn't really make any sense because you get an equation that b plus w2 is greater than 0, and you get b plus w1 is greater than 0. We also b has to be negative, so that equation tells us that w1 and w2 both have to be positive, but then b plus w1 plus w2, knowing w1 and w2 are both positive and b out of one of them is greater than 1, but you have to say that's less than 1, or less than 0, so that just doesn't make any sense.
Perfect. Oh man, that's actually a better explanation than I could have come up with. All right, so just to sort of re-summarize your explanation for the recording. Yeah, so this one is, the XOR is of what we call not linearly separable. And so there's a couple ways to show this. Come to that in a minute. There's a couple ways to show this. One is just a graph way. If we graph it, basically we have x1, one axis, x2, 0 axis. We see that we can't really draw a line where we can't really draw a straight line because this is a linear classification. We can't draw a straight line where we get only one class on one side or the one class on the other side. But exactly, the logical explanation makes perfect sense that Dominic said. Basically, we have a bias. We know that if x2 goes from 0 to 1, we want the function to shift from 0 to 1. We know we have this row telling us if x1 goes from 0 to 1, we want the function to shift from 0 to 1. But we also have this row telling us that if the x2 shifts from 0 to 1, we want it to go from 1 to 0. So there's a logical inconsistency, right? This isn't linear. It's dependent on, this isn't a linear function anymore because depending on the value of the other guy, this guy has to change its classification. This guy has to change the classification depending on how it shifts. This guy has to change the shift depending on the shift in classification. You guys know what I'm saying. So from that standpoint, XOR is not linearly separable. So that is a major issue with linear classifiers. I mean, not all functions, and not all data is going to be linearly separable. In fact, a lot of data is not linearly separable. So there are mathematical ways to prove linear separability that we won't get into the course, but that's sort of, I wanted to bring that up. As a quick aside, we could do the trick we did with polynomial with XOR in particular, and this isn't true for all non-linearly separable data sets. In fact, for most non-linearly separable data sets, you can't do this. But for XOR in particular, you could do the trick that we did with polynomial regression, which is instead of having the features be z is equal to m0 plus m1 x1 plus m2 x2, you could make the feature, you could map each of those values to a different feature space, to a different feature, to a different function, right? So with the polynomial fitting with the feature maps, we defined a feature map that was, instead of x1, x2, x3, it was x squared, x cubed. You could do something similar here. Define a feature map where you have where you have basically m0 plus m1 x1 plus m2 x2 plus m3 x1 x2. Okay? So in that case, you have 4 features that you have to optimize for. Not a huge deal, but how does this help us? Nope. Nope, I didn't put the answer. So this is just for us. In this room. Maybe I should put this on the midterm. Maybe not this one, but this one is like a brain teaser one. They make terrible exam problems. But what would the values of W0, M, right? We were using the value, what were we using? No, yeah, W, yeah. What would the values of B, W1, W2, and W3 be to make this whole thing work, you think? B, W1, W2, W3, yeah. Yeah, please, Kobe.
If you make B something negative, like -1, then
Yep.
W1 and W2 would have to be something greater than -1, so like 2. And then
Okay.
W3, you'd have to be something really negative, like, I don't know, -6.
Okay, yeah. So, I mean, you're pretty much bang on. So, I'll modify your answer slightly so we avoid the 0 case. But if we make B -0.5, let's say, and then make x1 and x2 both 1, right? That covers these two. That covers these 2 rows, right? If B is -0.5, if both of them are 0, we get a negative, and so we output a 0. If B is -0.5 and M1 and M2 are both 1, then we get a positive 0.5 here, so we get a 1. We get a positive 0.5 here, we get a 1. Then, for x1 and x2 being positive, so since both of those slopes are 1, then B is -0.5, so then we get B plus M1 plus M2 is equal to 1.5. So all we could do is say M3 is -2, bring it right back down. That covers all of the issues, right? We get a 0 again. So, yeah, kind of a nice little reminder of feature maps that the feature map doesn't have to be just the variable, right? The feature map could be combinations of variables. It could be functions of variables, whatever, right? That's the reason we did the whole the function vector calculus stuff. We covered it because you could do all sorts of different feature maps and define those as vectors, and then do all the gradient stuff. Same way as we do it with just when the features are just x1, x2, x3. Yeah. Okay. Good. Nice little brain teaser though. Let's see. Okay. So linear classification. So suppose we have the following data, and we're just representing the data a little differently now. It's not that different. But again, we have some x values, and then we have their targets, right? And in this case, we just defined a synthetic data set where when the x values are mostly positive, when the x values are positive, the out values are positive. When the x values are negative, then the out values are negative. Okay? And instead of 0 and 1, we're gonna define the targets as 1 and -1, and that'll become clear. In a moment. But again, it doesn't really change anything. Instead of going 0 and 1, positive samples and negative samples, we just have 1 and -1. Positive samples, negative samples. Makes more sense when you really think about it. We use 0 and 1 as a consequence of MOSFETs, but you know this really makes more sense. Anyway, so suppose we have the following data, and then we do a linear classification, and so we do the same steps as normal. We have our we solve our optimal matrix solution for the linear regression model. Because remember, we first have the linear model, and then we have that classification layer on top of it that interprets the linear model that says, when linear model is positive, we output a 1. When linear model is negative, we output a 0, right? So we just have to fit the linear model in a way so that it outputs a 1 when we get a 1 and a 0 when we want a 0. So again, we could use this little matrix solution and like so, and we fit a linear model to that data set. Okay. Seems to work fairly well. Basically, we have this linear model, and we have the little classification on top of it. And so whenever the linear model is positive, we have a positive classification. When it's negative, we have a negative classification. And overall, makes sense. The slope is roughly, I mean, really, the linear model is y equals x, which, given the synthetic data, I mean, given how it's generated, that's pretty much bang on. So all of that makes sense, I think. No really issues there, right? So let's now extend our data. Let's say we had someone else went into the field collecting more data, and came and added it to your graph after the fact. So we have more data, and I mean, really, it didn't really change much intuitively. Our pattern recognition brains in our head look at this and say, well, everything still fits. So, that's nice, but I mean, you can't always look at the data, so you'll go through the same process again. Do the matrix fit, and you get a new linear model, which is there. So this does not seem ideal, because now some of these are going to get misclassified. Basically, some of these are going to get lower classified, and the slope of the linear model seems completely wrong, right? I mean, it makes some sense. It makes some sense because, it's trying to average out these data points, it's trying to fit these data points, it's trying to fit these data points, it's trying to fit these data points, and all the linear regression is doing is saying, just find a linear model that fits all these data points. That makes sense, but it's not right. Right? It doesn't seem right. The model's getting pushed around, and namely, it's getting influenced by the extremes. So, linear regression. It's not optimal in this case, right? All right. Well, so the question is, what do we do about it? So, what do we do about it? We have multiple things we could do about it, but the first thing we're gonna try to do about it is support vector machines. The first thing we're gonna do is use a technique or a model called support vector machines. So we're gonna leave this data for a second. We're gonna discuss support vector machines, and we're gonna come back to it. Okay. So, what are support vector machines? The big issue was with the previous graph was that all the points contributed equally to determining the boundary between the positive and negative values. the positive and negative samples. So again, looking at this model, we have really, the boundary should be just a line straight up, right, like there, right? Something x is a billion, like the model should be y is a billion times x or something like that, right? Something here, it should be a nearly vertical line separating these 2 points. But the reason it's not a vertical line is that these points are pulling the linear model towards them, and therefore the slope gets altered by the points that are very far away, by the points that have very high value of x, but are still the same classification as these points here, right? So this does not seem right, right? Really what we want is to find the points that are near the boundary, and those are the points that should influence the boundary most, right? That's how we have 2 different classifications, and at some points the classifications are going to be close or even overlap. And really, those are the points that matter for the boundaries. The extremes are kind of irrelevant. The extremes will be fine, will be classified correctly regardless. But classifying the points at or near the boundary, that's the challenge. That's the whole point of classification, right? The whole point is to create a boundary, and really the boundary, the most important points for the boundary are these that are around it, okay? So that's the idea behind support vector machines, that you have a graph, and instead of the 1D graph we were using before, we're using a 2D graph now because it's visually more pleasing and easier to understand. So we have a 2-feature graph, and again, we have a boundary. We want our model to fit a boundary that separates positive samples from negative samples, okay? But the issue is that, what we're going to do here is basically we want there to be sort of a margin around this boundary, and we want to tell our model, okay, if there are points inside or on the margin, these are the points that you should focus on shifting the boundary to account for, okay? We want to get as many points outside the boundaries as possible, while also getting the points on the correct side of the boundaries, right? So we don't care about these points. We shouldn't use these points in the calculation. These are outside the boundaries, and they are already correctly classified. But these points that are on or near inside the boundary, these are the points that we should use to calculate how to alter the boundary condition here. Okay? So we have a boundary condition, and again, we're defining it as W times X, where X is the actual inputs plus the 1 column. We have that boundary condition, and now we just alter the boundary condition slightly to be, from the boundary condition, we want this boundary is defined as W times X is equal to 1, and this boundary is defined as W times X is equal to negative 1, okay? So we're just increasing the size of that boundary, and again, this we could directly have a boundary variable like width, I think. That would be like BW. We can have a BW. This W times X is equal to negative BW. W times X is equal to positive BW. But then we put it on the other side, and it will get absorbed by the bias term anyway. So it's not really necessary. Major thing, we just want the boundaries to have a certain width, okay? And we want the model to optimize the width of the boundaries. Okay? So how do we define this? Oops, there we go. So let's assume that the blue circles here are, let's assume the positive samples are +1 again, and let's assume the negative samples are negative. The negative samples are equal to -1. Okay, it makes the math work better. So for each negative class, I should say negative sample. For each negative sample, we want, or for each sample, we want w times x to be greater than 1 if the sample is positive, and w times x to be less than -1 if the sample is negative, if the true sample is negative, right? So we could rewrite this another way. We could rewrite this as t time. We could rewrite this as, we could use this actual label to rewrite this condition as t times wx is greater than 1. That makes sense because t is 1 in this case and wx is greater than 1. We could also, if we multiply this side by t, then we could also rewrite it like this, because if t is equal to -1, then t times wx is greater than 1. I mean, -1 times wx is supposed to be greater than, sorry, let me rephrase this. For the negative sample, where t is equal to -1, we still want this condition. Namely, if we have that negative sample and we multiply this by -1, we flip this sign, and we still want t minus, we still want t wx to be greater than 1. Okay? This also works in reverse. Namely, if we put this to the other side, yeah. Yep, that works. Okay. So if we have this condition that holds true, that's basically the same condition for both cases. We have this case, wx is greater than 1 if t equals 1. That also means, I mean, we could just add t to the equation. We don't change this phrase here and this are equivalents. Then also, if t is equal to -1, this here is equivalent to this here, right? So so this condition captures both these cases, this one condition. That's kind of the clever thing here. This one condition here captures both what we want for the negative when t is negative and what we want for when t is positive. It's kind of nice. That's the clever thing about classification classifiers, and we'll see this also in logistic classifiers, that we could rewrite both these conditions as a single inequality. Okay? And then from this inequality, we could also, well, it's always nice to have 0 on one side of the equation, so we also just move this to the other side to get 1 minus t times wx is less than 0. Again, everything follows neatly from this one leap, that basically you could represent two conditions here as one inequality, okay, by just including the classification label in that inequality. Okay? So, this inequality right here is satisfied as long as wx is greater than 1. Right? And as long as wx is greater than 1, then this value here is greater than this, and then the whole thing becomes negative, which satisfies this inequality, which is less than 0. Okay? But beyond that point, really, who cares? That's the real point. As long as wx, as long as this is negative, this whole thing, the sign of this whole thing is negative, we're happy, right? As long as we're happy, but we're happy only as long as Wx is greater than, the absolute value of Wx is greater than 1. And if t is positive, we're happy as long as Wx is greater than 1. If t is negative, we're happy as long as Wx is greater than negative 1. I mean, is less than negative 1, right? So if we only care about the values that are within this parameter. Oh, before I go down. But if Wx is something less, if the magnitude of Wx is something less than 1, let's say Wx is equal to negative 0.5, okay? If Wx is equal to negative 0.5, then, then negative 1, then if the sample is a negative sample, then we have negative, so negative positive 0.5, and then this whole thing, 1 minus positive 0.5 is equal to 0.5. So it's a correctly classified, but we get a non-ideal amount, okay? So what we want to do is penalize the model when this whole thing is not satisfied. And we do that by basically taking the max of 0 t times Wx minus Wfn. Oh, it should be 1 minus. That's why I'm tripping up. I was like, what the hell is going on? All right. I don't even know why it's rendering like this. Okay. Something's wrong with my renderer. I think something happened with the Rise rendering right now. So, oh, I will fix you later. But for now, I'm gonna make your necessary changes. Okay. So so we want the max of either 0 or 1 minus t of n Wx, whatever. Okay? Oh yeah, 1 minus t Wx. Okay? So t minus Wx is 0 as long, I mean, t minus Wx, the only way to be greater than 0 is A, if this is misclassified, right? If this is misclassified, let's say this is positive and we have a negative value here, then we get negative times negative is positive, positive, positive. So then the max function will be something positive, a positive value greater than 0, if this is misclassified. Let's say that it's actually, it classifies it as negative, but this is a positive sample here. Let's say this is something negative, this is a negative value, this is a positive value. So then we get negative times negative is a positive, 1 plus positive is something positive, so we get a positive there. So the only way for this max function to output something that's greater than 0 is if A, if it's misclassified, or B, if it's classified correctly. Let's say it's a negative sample, but also Wx is negative, so negative, 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 good. But if the magnitude of Wx is not greater than 1, let's say it's 0.5, then we still get 1 minus 0.5, which is positive. It's not as positive as a misclassification, but it is still positive, right? And so in this case, we'll still get something that's not 0, something that's greater than 0. Okay, so remember what we're trying to do with the loss function. We're trying to come up with a function that basically gets larger. It gets larger when the model is doing something we don't want. Okay, and so A, we don't want our model to misclassify data, and B, we don't want our model to have data points very close to the boundary. We want the boundary to be far from the data points. Okay? So this does both things. both. It gives a positive value when something's misclassified. It gives a positive value when something is within that boundary, when a data point is right on that boundary. It could still be correctly classified, but if it's within that boundary, within those margins, you still get a positive value. So if we do this, so if we square this, always with the squared mean error loss, we want to square it to make sure we don't get any negative values. Although in this case, I'm not sure that's necessary, but still, it's nice. So as long as we square this, we get a loss function that basically increases the more data points that are misclassified and increases the more data points that are closer to the margin, that are farther away from margin. And if something is correctly classified and something is far away from the margin, let's say something was a negative sample, -1, and then the magnitude of Wx is very negative, is less than -1. Let's say it's -2. So negative, negative, negative. So all those cancel out to get negative, and then that would be 1 minus 2, which would give us -1, which would output a 0. Okay. So if something is correctly classified and the magnitude of the classification is larger than 1, then we get a 0. And that would be the bottom, the minimum value of our loss function would be 0 if everything is correctly classified and everything is outside of the margins of the boundary, then we would have a loss function of 0. But if some things are misclassified or some things are within the boundary, we would still get a loss function of positive. We would still get a loss function, some positive loss function, and then we could use PyTorch to minimize the loss function by adjusting the W parameters and do things that way. Does that make sense? So that's why it's called a support vector machines. You have a boundary and you have some support vectors, and it's helping you adjust the boundary. It's helping you adjust the boundary by caring for all the data points that are within the support vectors and not really focusing on the data points that are way outside the support vectors that are correctly classified. Those data points, it's covered. We only care about the data points that are not correctly classified and the data points that are within the boundaries, because, again, the data points that are close to the boundary, you want to adjust the boundary a bit. You want the boundary to be very far away from all the data points, if possible. Does that make sense? Yep. All right. So we have one more optimization. I know that's the hardest thing to understand with support vector machines. Well, the hardest thing is understanding how that one inequality could represent both cases. But as long as you get that, everything flows kind of nicely. But also the loss function. So we have the loss function we had this loss function. Whatever. We had this loss function here. The other thing that you really do need, and the only way for you to really internalize why you need this is to play around with it. But you need to have the model adjust the width of the margins. Okay? Because again, you want the margins to be as wide as possible, right? And so if you do out the math here, so the margins, you have this, and so if you do out the math, the margin, the distance from this point to the corresponding point on the margin, assuming a 90-degree line, the distance between these two is equal to 2 divided by the length of the vector W. This is because, we want the top line has a formula Wx1 is equal to 1. The bottom line has a formula Wx2 is equal to -1. So then we combine both functions. W times x1 minus x2 is equal to 2. We omit the bias term. The bias term gets canceled out when we add Wx1 and Wx2 together. So that's the reason for this right here. And so that means that x1 minus x2 is equal to 2 over w. So the length of the distance between x1 and x2 is equal to the distance of w. Okay, so the absolute distance is just the 2 over the absolute distance of w. So we want to maximize this margin. We want the margin to be as large as possible. We want to basically get the separation between the positive and negative data samples to be huge as possible. So another way to say that is that we want the inverse. We want to minimize the inverse of this, right? Loss functions, PyTorch is set up to always minimize values. So instead of saying we want the maximum of this, we say we want the minimum of this. Okay? So hopefully that makes sense. So you add this term to the loss function, and then you add a term c to basically prioritize either maximizing the margin or classifying all the data points correctly. Okay, so you have two different competing interests. You could either adjust the boundary condition so that more data points fall on the correct side of the boundary, or more data points fall outside the margin or inside the margin, whatever. So you could adjust the boundary to do that, or you could actually just adjust the margin. Okay, so two competing interests. So you typically need a fitting parameter to sort of weigh those two interests. And then it's just a matter of playing around with the fitting parameter to get something that looks good. Okay, so let's see how this works in practice. One thing I want to point out, scikit-learn has some amazing data set tools, and one of the more cool things is that it has a sample data set creation for classification. So you could test how well your model classifies data points. So nice little function there to use. So that's how I'm creating the synthetic data here. So there we go. So again, doing the same thing as before. I have some sample data. I have the labels, the target labels. So I'm doing a 2D classification here, x1 and x2, similar to the diagram. I'm just trying to replicate the diagram I drew in the previous slide. So I have two parameters, a bias, and then, oh yeah, here. So we modify x to include the bias term and the actual parameter inputs. And then we just do the same thing. We define the error, we define the actual loss function, which is simply that margin term. That margin term times the max function, that little max function here. And then we simply do gradient descent. We do back propagation on that loss. We adjust the parameters as normal. All of this is copied from previous lectures, and then we plot out the lines that we get, the boundaries that we get. All right. So if we do all of that, so for instance, this is a synthetic data set. This isn't quite as clean as what the image I drew out, but you can see some clear categories. You can see two clear categories, a group here and a group here, and you see the boundary is pretty good. I think the boundary is drawn pretty good. It's a little, it misclassifies a couple blue points here, but that's also because there are a couple red points here that's impossible to get to without misclassifying more blue points. So this is the optimal points. And then you have the margin lines, which again, you have most of the points outside of the margin, a few points inside the margin, but especially for the negative samples, it does a good job of getting that margin, of getting most of those samples outside the margin. And the only examples that are within the margin are sort of, I mean, really, it's hard to adjust the margin any more than that. Yeah, but sort of looks very similar to our theory, right? So we could be confident that it works. Other thing is that you could adjust, if you want, you could adjust the random state here to get different data points and see how the support vector machine classifies the data, how it draws a line. Oh, and also you could adjust the C parameter here. Yeah, so play around with it, have fun. But yeah, so it seems to be working pretty well. Okay, so that's good. It means our theory is correct if we could show that it works in code. So that's good. And then let's go back to our motivating graph, remember, from so many slides ago, what seems like an eternity. We have a bunch of data we have a one parameter data set. So basically the data set that we created, and if we go up here, the idea is that if the x is negative, then we want it to classify it as negative. If x is positive, we want it to classify it as positive. That was the synthetic data set we generated before. So we plotted that. And again, if we run the support vector machine, we get something that's pretty good. We get basically a boundary, and we get the support vectors, and we get all the lines outside of that boundary. So everything seems to work well. So the linear model, and again, I mean, intuitively, we said that the optimal linear classification would be basically if z was equal to like 1 billion times x plus 0, really. There's no bias here. And that's pretty much what we get. Well, not 1 billion, but it's basically z is equal to 8 times x, which, I mean, there's plenty of space. So it's a pretty high slope, so everything works out pretty well. Yeah, makes sense? All right, so that's what support vector machines are. Not difficult. The only sort of difficult thing in support vector machines is knowing how to represent multiple boundary conditions as a single inequality, and everything flows quite nicely from there. And also the other thing is that support vector machines, the idea behind them is simply that you have you have a boundary, but you have margins around the boundary. And so you make your loss function consider the margins. You make your loss function so that the data points within the margins are considered, the data points that are misclassified are considered, but the data points that are correctly classified but fall way outside of the margins, those aren't considered. Okay. Okay. There we go. Okay, so I'm missing one plot. Oh, that sucks. One of the plots that I made last night didn't make it its way into here. All right, anyway, no worries. Okay, so now we could move on to a different type of classification model. One of the more, I mean, you don't see support vector machines. Oh, no, you do. Also, by the way, scikit has a support vector machine function, like library. So you don't really need to go through the whole gradient descent and all of that we did. This was just for us, just to show basically the idea behind of it. But scikit has a support vector machine classifier that works fairly well. So yeah, you're never going to see people manually code up support vector machines, especially not in PyTorch. But it's good. It's learning. We're learning. All right. So now we're just going to do logistic regression. So looking at this model again, I mean, like the shape of this model pretty much gave away that it looks like the sigmoid model, which we discussed many lectures ago, right? this graph like looks exactly like the sigmoid graph that from, I mean, I think it was lecture 3 or 4 that we first introduced sigmoid function. So, I mean, it's only natural that we do, that we use that function. So that's what logistic regression is, using the sigmoid function, using a nonlinear function to classify points, okay? So again, we have the sigmoid function that basically goes between 0 and 1. 0 and 1 given that a particular input or set of inputs, right? So again, this right here within the exp term, this is still a linear function, right? This is still m1, I mean, this is still bias plus m1x1 plus m2x2 plus m3x3. This is still a linear function within it, but you just have a nice little wrapper around it that says 1 over 1 plus the exponential of that linear function. And so if this linear function is huge, if this linear function is huge, if this linear function is huge, then this whole function, this part goes to 0, this whole function goes to 1. If this linear function is small, then this part becomes big, this whole function goes to 0, right? So depending on the size of wx plus b, you go from 0 to 1, right? That's how the sigmoid function works. So how do we use this for classification? That's the question. So we have a couple annotated data points. Oh, yeah. We have a couple of data points. So we have a data point, we have a couple data points with a label of 1. And we want, whenever the data point has a label of 1, we want the sigmoid function to be as large as possible, i.e. we want it to be 1. Whenever the data point has a label of -1, we want the sigmoid function to be as small as possible, i.e. we want it to be 0, right? Same ideas as before. I mean, before we defined it explicitly using a piecewise function when the sign of the linear function was +1, we wanted 1. When the sign of the linear function was -1, we wanted negative. When the sign was negative, we wanted -1. Same idea, okay? The only difference is that instead of that piecewise function, we're wrapping this function, we're wrapping the linear function up in a sigmoid function, okay? And so whenever the annotated data point has a label of -1, we want the sigmoid function to be as small as possible, i.e. as close as possible to 0. So the last point we could be formulated differently, that whenever the annotated data point whenever it's a negative sample, we want 1 minus the sigmoid function to be as large as possible. So to be 1, which is equal to 1 plus the exponent of wx. Okay, that makes sense. This is hearkening back to what we discussed in the support vector machine. So if we have two conditions, one, if the label is positive, we want this whole function to be as large as possible. If the label is negative, we want this whole function to be as small as possible. We want this whole thing to be as small as possible, which means we want this whole thing to be large as possible. Okay. So what does that give us? It gives us basically representing two conditions as a single boundary, as a single inequality, same as we did with the support vector machine. We use the label of the data point. And basically, when the label is positive, we want this one to be as large as possible. Makes sense? When the label is negative, then this label, everything still works out, because then negative times this negative, we get this, and we still want this to be as large as possible. Okay? So we want to maximize this function. Does that make sense to everyone? So again, we're doing this basically the same thing we did with the SVM. We just are doing it with the sigmoid function, and we're representing multiple conditions as a single function using the data label. Okay, so this is probably old hat to you guys, but just in case. Because the function varies between 0 and 1, we think of this as a probability curve. You've seen this probability. You've seen this sigmoid probability curve a lot, probably, in your studies. So it's useful to think of this thing. We could just call this a probability curve, a cumulative distribution function, and we just label this as this whole thing is the probability that given x, that all the labels of y are equal to y. Okay? And so we could just rewrite that a bit. We don't have to be so explicit constantly. We could just write some shorthand. In fact, this is the way it's normally written in textbooks. And then we have to expand it for every single data set. So if we want to basically minimize or maximize this probability for multiple data points, it is a probability. So because we're dealing with probabilities instead of actual values, it makes little sense to add probabilities together, like adding 25% plus 50% plus 83%, that sort of thing together. No one does that. It doesn't make sense. So instead, we're just going to multiply the probabilities together. And we want to try to get all the probabilities multiplied together to be as large as possible. Okay? So that's what we're doing here. We want the argument max. We want the values of W where the probabilities for every label is maximized. For every label in D is maximized. The multiplied together is maximized. And then we want to play around with this a little bit. And the main thing we want to do is look at ourselves and say, well, it doesn't change anything to maximize this function directly or maximize the log of this function directly. I mean, the W for this, the value of W, the value of the parameters for the max of this function will still be the same value of the parameters for the maximum of the log of that function, right? It's just a difference, it just scales differently. So we're going to add in the log here, and instead of, we're adding in the log, and then of course, when we're multiplying logs together, when we have the logarithm of multiple values of when we have the logarithm of something multiplied, of A multiplied by B, that's equal to the logarithm of A plus the logarithm of B. That's a log identity. So this product, so since the log is outside the product here, now we get a sum of logs. We take this product, we bring it outside the log, make it into a summation. So now we get a sum of logs. And instead of maximizing, because again, PyTorch likes to minimize functions, instead of maximizing, we add a negative sign to minimize this whole thing. Okay, makes sense? So all of these little steps make sense on their own. And then of course we replace the probability curve here with the actual, with the probability function with the actual function there. So all of this on its face makes sense, right? Yeah, and because, I should mention, and because we had this function, the actual probability function was 1 over this, but because that's 1 over, so log of 1 over A is equal to negative log of A, right? Because this deals with, again, log identity. So that's where this negative went. That's where this 1 over went. It got canceled out by this negative here. Okay? So each one of these steps, each one of these is a little step, but we get from just here, or something, we get from this sigmoid function here to here, taking a bunch of little steps, but all these little steps together allow us to really get a nice little loss function going, right? So we have to find the values of w that minimize this function. So of course, this becomes our loss function. Well, this becomes our loss function. If we wanted to, we could take the gradient directly. This is, I think, previous semesters, they took the gradient directly by taking the derivative with respect to w and doing all of this. I was a little tired last night. I didn't want to go through and manually calculate the gradient, so I just made the loss function. I just made the loss function directly. So again, same code as before. This boilerplate. I'm sure you guys are tired of seeing this boilerplate, but again, this is our synthetic data. If x is negative, then we want negative. Then we want the classification to be -1. If x is positive, we want the classification +1, just to generate some synthetic data. And again, all we do is this loss here that we defined in the previous slide. This sum of the log of the sum of all the data points, where for each data point we calculate the log of 1 plus the exponential of x times WGD. And we have one parameter, so the 1w plus the bias value. Okay? And so we just change around that log. We do all that good boilerplates in math, and there we go. And we get something that looks pretty reasonable, right? We get a logistic function that gives you a 1 every time the data set is equal to 1, the classification is equal to 1, and a 0 every time the classification is equal to -1, which is what we wanted, right? So, yeah. So that's logistic classification. There's more to it. There's more caveats to logistic classification, namely the types of loss functions, how we could fine-tune it, how we could do it for multiple classes. But this actually served as a good input. So I will stop there. Ooh, right on time. That's surprising. So we'll stop there. Have a good weekend. Homework 4 is due Monday, and then we'll we'll continue talking about classification and logistic regression Tuesday, and then we'll go on to, I think, PyTorch optimizers and stuff after that. Yeah, have a good weekend, guys.